So, we are now going to continue our discussions on MAC protocols for MANETs. So, we are in the second part of the lecture. So, we have already discussed two well known protocols, which is the MACA protocol and the MACA-W protocol for use in MANETs. There is another protocol which is called the DB TMA protocol, which is also very popular. So, the MACA protocol or the MACA-W are single channel protocols. That means that the entire bandwidth is treated as a single pipe. So, DB TMA belongs to the multi-channel class of MAC protocols. So, in DB TMA what happens is the entire pipe, the bandwidth is basically fragmented or split into multiple channels. So, some of these channels are used for sending the control packets, whereas the other channels are used for actually sending the data packets out. So, this is how collision is reduced with the help of splitting of the channel into multiple sub channels. So, now let us look at the different features of DB TMA. So, incidentally, DB TMA was proposed by two researchers, Zygmunt Haas and J. Deng at Cornell University, and so what they have observed that the probability of CTS packet being destroyed could be as high as 60% for high traffic load in multi-hop networks. So, this is why they have proposed the DB TMA protocol as an enhancement over the existing MAC protocols. So, as I told you at the very beginning, so we have a common channel, one single pipe that is split into different sub pipes or sub channels, the data channel and control channel. The data channel, as the name suggests, is used to transmit data, whereas the control channel is used to transmit control packets like the RTS, CTS frames. So, these should be called as frames. So, there are two out of band busy tones that are used to notify nodes of ongoing transmission. So, these are the two. One is known as the transmit busy tone PTT, the other one is known as the receive busy tone BTR. So, this is basically almost similar to, I do not know, those of you who might have little bit of understanding about telephony applications. This idea has resemblance to how the telephony applications work. So, two types of tones, transmit busy tone and the receive busy tone, two of them are used. So, the BTT is set up by the RTS transmitter to protect the RTS packets. It indicates that a node is transmitting on the data channel. So, BTT, right. So, transmit, right. So, transmit busy tone. So, it indicates that the node is transmitting and transmitting on the data channel. Receive busy tone is set up by the receiver to protect the incoming data packets continuously. It indicates that the node is receiving on the data channel. So, BTR stands for, R stands for receive and T stands for transmit, and both on the data channel. The two busy tones are sine waves at two different frequencies with enough spectral separation to take care of issues of inter-signal interference and so on. So, broadly these are the steps in DB TMA. So, we will look at the steps and we will look at the figure in the next slide. So, A sends an RTS to B, A sends RTS to B, B, if unwilling to receive, sends the CTS to A and turns on the BTR, okay. So, you see that this is how the BTT and BTR packet frame exchanges are depicted. Okay. So, B, if unwilling to receive, sends the CTS to A and turns on the BTR. Okay. So, it is going to turn on the BTR as shown over here. The neighboring nodes on hearing the BTR are blocked. The neighboring nodes will be blocked on receiving the BTR. The node A, which was the sender, turns on the BTT after getting the CTS. The neighboring nodes hearing the BTT are blocked and they ignore any transmission received from A. A then sends the data to B and both turn off the BTT and BTR after the data exchange is over. So, let us now look at the figure once again to convince ourselves the steps that we have just seen. Okay. So, node A sends RTS, CTS back to A by turning on the BTR by node B, and then the data exchange takes place after A receives the copy of the frame. So, let us look at little bit in more detail stepwise how this thing is going to function. So, let us now focus on the slide. So, let us consider that we have a group of nodes A, B, C, D, E, F and G as shown in the slide. So, then let us assume that node A wants to send data to node B like this. So, the area covered by node A is depicted like this, the circle, the blue colored circle that you can see. That means that nodes E and G are in the transmission range of A. So, along with B, these are also going to get a copy of the frame that is sent by A to B. Node E in this case is the exposed station and node C is the hidden station, obviously. So, there is no doubt about it. Node A senses the control channel. Node A senses the control channel for the BTR and BTT signals before this particular node acquires the data channel. Okay. So, it senses the BTR and the BTT signals, the control channel for the BTR and BTT signals before actually sending the data channel data over the data channel like this. Then if no control signal is found, node A activates the BTT and sends a RTS packet to node B. Okay, like this. If control signal is found, node A activates a random timer and tries again later. As you can see, the timer is activated by node A, and then after the timeout it is going to attempt transmission once again. Now, node A turns off the BTT, activates a timer and waits for reply from node B. Clear? Now, node B receives the RTS packet, it senses the BTT and BTR signals. If no control signal is found, node B turns on the BTR signal and sends a CTS to node A. Okay. Node A receives the CTS and turns on the BTT signal. Node A then starts sending the data packets. So, basically it is the introduction of the BTR and BTT and complicating the control phase. Instead of sending simple RTS CTS, complicating it little further to ensure that there is lesser number of collisions, chances of collisions that can take place by using the previous MAC protocols. So, after that data transmission is over, node A turns off the BTT and node B then turns off the BTR. It turns off the BTT and node B is the receiver, so it turns off the BTR. So, that means that you are gracefully turning off the control signals that were activated before after the successful transmission of data. Okay, like this. So, what we see over here is the the state chart of the DB TMA protocol. So, the ellipses basically denote the different states in which the protocol is going to be at different instants of time, and the transitions are shown in the form of directed arrows. So, these are the different states of operation of DB TMA. So, it is either going to be in the idle state when the node with no packets to send stays, this is called the idle state, and then or it can be in the content state where the node has data to send, but it is not allowed to send the RTS. So, it stays in the content state, or it can be in the SRTS. So, the node sending the RTS is in the SRTS state, S data node sending the data is in the S data state, WF BTR, WF data and wait states. So, these are all different types of states. There are 7 different states in which the protocol, the DB TMA protocol can operate. The protocol obviously has different advantages and disadvantages. So, although some of these hidden terminal and exposed terminal problems are solved, but still there are issues such as with respect to the overall performance, we are using more number of packets, etc., etc. So, these different issues still remain, and the overhead, the control overhead basically increases in the network. So, there are some problems. The problems is that there is requirement of additional hardware to generate and receive busy tones, and the bandwidth consumption, as I said just a few minutes back, of the busy tones is not negligible practically. So, so the overhead is going to increase. So, next protocol that we are going to discuss, it is known as the MARCH protocol. It stands for multiple access with reduced handshake. It was proposed by CK2 in 2000. It exploits the properties of the omnidirectional antennas and overhearing properties of MANETs. It reduces the total number of RTS CTS handshakes and combines the advantages of both the sender initiated and receiver initiated protocols. So, earlier we have seen both the different types of protocols, the sender initiated protocols and the receiver initiated protocols. This is kind of a hybrid between the sender initiated and the receiver initiated protocols. So, so we are going to not go over the requirements for MARCH, but let us understand few basic concepts before actually going through the different steps of execution of this protocol. So, the CTS packet is used to convey information to the next node about data packet to be received. The next node can initiate invitation to forward the data to itself. So, it is request first and then pull later kind of mechanism. The RTS CTS handshake is required only at the first hop, the CTS only handshake from the next hop. The total number of handshakes reduced from 2L in MACA to L plus 1 in MARCH, where L is the number of hops in the route. So, this is an improvement. The MARCH has improvement over MACA in terms of reduction in the total number of handshakes that are required. So, MACA required 2L number of handshakes, whereas MARCH requires only L plus 1, and obviously so MARCH basically reduces the number of handshakes that are required. RTS CTS basically contains MAC addresses of the sender and the receiver and the route identification number. So, let us now look at this timeline diagram. So, we have 4 different nodes A, B, C and D. And let us look at this scenario of transmission and the steps that are there in MARCH. So, let us follow the different steps. So, let us assume that A the node A, that means this particular node, sends the first RTS1 to node B. So it is like this: A sends first RTS to B. B receives and sends the CTS to A. B receives and sends CTS to A. Node C basically gets a copy of it, overhears it. So CTS 1 was sent to A, but C is in the direct transmission range of B, so it basically gets a copy of the frame. So C overhears the CTS 1. B does not send the RTS to C. C waits for the time TW, allowing B to receive and process the data. C sends the CTS2 to B to invite B to forward the data packet. B sends the data to C, and RTS2 is then suppressed here. So B sends. So as you can see over here, that these timers, two different timers are used, and after that basically the corresponding CTSs are initiated. So it is not like, so we had the CTS1 that was sent from B, which was overheard over here, and the CTS2 was again sent by this overhearing node, and a copy of it again was received at D CTS2, and after the transmission of the data, so this CTS3 is initiated from this overhearing node D. So if there are multiple routes, which is quite common in ad hoc networks, so this is what is going to happen. Node C in this particular example, so here what we have a scenario of A, B, C, D, and two routes A, B, C, and D. This is one route, route 1, which is shown in the green color, and the other one is X, C, Y, which is black colored route that we can see in this particular. So two different routes, overlapping routes in the case of this particular network. So node C in this particular case is common to both route 1, that means A, B, C, D, and X, C, Y, route 2. A sends RTS1 to B, A sends RTS1 to B, B sends CTS1 to A, C overhears the CTS1. So this is something that we have seen in the previous slide itself, so that is nothing new so far. So C overhears the CTS1, gets the information about the sender B and the route ID. The timer TW is started at C until B receives and processes the data. So this timer is initiated, initiated at C. Upon timeout, C basically sends the CTS2 to B, B sends the data to C. Similarly, D sends CTS3 to C, C sends data to D, and these CTS packets are overheard, CTS2 packets are overheard by A and D, which check the route ID and they discard these overheard packets, the overheard frames more precisely. So this is how these two different multi-hop routes with common nodes are basically, this is how it is handled using the March protocol. So it also has some additional features. So in March, the MAC layer has access to the routing tables. So it is a cross layering kind of approach, which maintains information about the routes in which a node participates and its neighbor nodes, because this is essential. As we have seen in the previous case, we have multiple overlapping routes, right? So the routing information has to be, routing table information has to be made available at the MAC layer, right? So it's a cross layering approach. Then the CTS only handshake contains route ID for the route the node is participating in. March gets information whether to respond to a CTS from the routing table information. March only consults these tables and does not perform routing. So, March basically is a MAC layer protocol. So, it only gets access to the routing table information from the network layer, but it actually March does not take care of routing specifically. So, these are some of the advantages, so obviously the throughput is increased, the control overhead is reduced over the MAC protocol and the primitive other types of MAC protocols for MANETs. So, these are the references. Again, as we have seen, so C.K. To's book as well as this particular guide to ad hoc networks published by Springer, these are quite widely available, and these books can be consulted for this part of the lecture. And additionally, the DB TMA protocol, it was published in the IEEE Transactions on Communication in 2002. So, if you want to understand this protocol in detail, you need to get a copy of this particular paper. And the March protocol was published in Milcom by To et al. In 2000. So, these are the two protocols that we have discussed in this part of the second part of the MAC protocols for ad hoc networks lecture. Thank you.